Hi everybody. Welcome to Universe View Odyssey channel. Dialogue concerning quantum entanglement of massive atoms. Q1. In the previous two videos, we looked at the Aspect team's experiment that confirmed quantum entanglement, and the research achievements of the 2022 Nobel Prize in Physics winners for their entangled photon experiments. All of their experiments confirmed entanglement using zero-mass photons. Then, is quantum entanglement possible even in atoms with non-zero mass? Q2. Possible. There are research results that confirm this. Still from an animation of a NIST quantum entanglement experiment. Recently, a research team from the Department of Physics at the University of Basel in Switzerland, Paolo Colciaghi, Yifan Li, Philip Treutlein, Tilman Zebold, has shown the quantum entanglement phenomenon in clouds composed of 700 rubidium-87 atoms. The study was published in the physics journal Physical Review X. Q3. Wow, the quantum entanglement that Einstein called spooky action at a distance. It is surprising that the entanglement was confirmed not only in photons but also in the massive atom system. Is this the first experiment of quantum entanglement of massive atoms, or is there another research result? Another study was reported earlier than this. In April 2018, Science, a world-renowned scientific journal, published 3 papers on quantum entanglement of massive atoms side by side. These papers are theses of the research team of the University of Basel, Switzerland, the University of Hanover, Germany, and the University of Heidelberg, Germany. Q4. In the meantime, since the Aspect team's experiment, we have known the phenomenon of quantum entanglement, so much that we do not doubt it. We even heard that a Chinese research team succeeded in experimenting with long-distance quantum communication up to 7,600 kilometers using quantum entanglement. However, all of these experiments used massless photons. Explain the outline of quantum entanglement experiments with these clouds of atoms. The concepts of these experiments are coincidentally similar. All of these are independent confirmations of entanglement between spatially separated clouds of ultra-cold atoms. The research team used a relatively heavy element, rubidium-87, instead of the zero-mass photon. The research team at the University of Basel cooled 700 rubidium atoms to a temperature close to absolute zero and made them into a Bose-Einstein condensate (BEC) state to begin experiments with massive atoms entanglement. The Beck state is a kind of cooled atoms cloud, in which all atoms behave like particles with the same properties and therefore have the same quantum state. The research team creates a Bose-Einstein condensed state and then entangles the spin state of each atom by inducing interactions between the particles. Then, when the traps confining the atoms are loosened, the cloud of atoms spreads out, eventually splitting into 2 smaller clouds, A and B. Q5. Now, we need to check whether the spins of the separated A atoms and the entangled spins of the B atoms are conserved or broken. How did the research team show this? To show this, the research team observed the specific spin state of the particles in each cloud by manipulating them using high-frequency waves. If entanglement is conserved, the spin state of the particle in cloud A should show a high correlation with the spin state of the particle in cloud B. This is because observing the spin state on one side immediately determines the spin state on the other side, and vice versa. The research team discovered exactly this phenomenon. Through entanglement, the research team confirmed that measurement of one part of the entangled system makes it possible to steer another part to a specific state, called quantum steering. A cloud of atoms is held above a chip by electromagnetic fields. The entanglement was observed between the spatially separated regions A and B. Illustration: University of Basel, Department of Physics. Q6. If quantum entanglement is not only a characteristic of photons, but also applies to materials with mass, it will be possible to say that the universe is spatially entangled. What are the implications of these studies? These studies are evaluated as opening a new door to quantum entanglement. In other words, it is sure to be a trigger for exploring quantum entanglement between massive macroscopic materials. Q7. Where can these studies be applied? Quantum entanglement is expected to contribute to the breakthrough of next-generation quantum technologies such as quantum computing and quantum communication. In particular, this research is expected to be applied to metrology, a science of ultra-precision measurement, as well as quantum computing and quantum communication in the near future by using entanglement of more particles than photon entanglement. Thanks for watching. You can read this story in injury time, injurytime.kr.